So today we continue with our discussion about representing chemical reactions. We've talked about writing equations and about balancing those equations. So today we're going to continue that discussion by talking about net ionic equations and by talking about particulate diagrams, which we use to represent the interactions of the molecules and atoms in a reaction. So let's start with net ionic equations. This should be a review, but we'll move through it fairly quickly, and I'll do a couple of practice problems with you. So when we want to write a net ionic equation, our very first step is going to always be to write the molecular equation. So step one, we're going to write a molecular equation. And we're going to go ahead and do an example as we move through this so that it's easier for you guys to picture and follow along. So we're going to write a molecular equation. So the example equation that I've picked for us today is that we're going to talk about combining iron 2 sulfate in solution with barium chloride also in solution. Okay, so we need to finish this equation. We have our reactants, we have our iron 2 sulfate and our barium chloride. And so this is going to be a simple double displacement reaction. We're going to exchange anions. And so we're going to wind up with barium sulfate. And since the sulfate is a -2 and the barium is a +2, we don't need any subscripts. And iron 2 chloride. And since the iron is a +2, we need 2 chloride ions to go with it. So we now have our balanced molecular equation. Well, let's double check and make sure it's balanced. I have 2 chlorides, 1 iron, a sulfate, a barium, and a barium. So we have a balanced chemical equation. Now, when it comes to determining the states, which is important when we write a net ionic equation, we need to know what state things are in. We need to know if either of these is insoluble. So we learned all of the solubility rules, but the beauty of AP chemistry is that we have some shortcuts, okay? And our shortcut we're going to call the SNAP rule. So the SNAP rule stands for sodium, nitrates, ammonium, and potassium. Now I know the potassium symbol is a K, but we use the P because by doing this, we can say SNAP, sodium, nitrate, ammonium, or potassium. If it contains one of those, it is soluble. Now, this doesn't apply to any of these, does it? So in this case, if this were an AP question, they would tell you which one of these would precipitate out. Hopefully you remember your solubility rules, and so you know that sulfates are soluble except with heavy group 2s. And barium is a heavy group 2, so this is our insoluble precipitate. So we're going to put an S there, and we're going to put an AQ here because we remember that the halogen salts are also, generally speaking, soluble. So we've written our molecular equation. The next step is to write anything that is an ionic compound that is dissolved in water as its dissociated ions. And so we're going to write our electrolytes as ions. And so we're going to write our iron 2 ions in solution plus our sulfate ions also in solution, combined with our barium ions also in solution. Now, we have 2 chloride ions. That little subscript 2 tells us there are 2 chlorides in this barium chloride, but there's nothing holding them together once they dissociate. In fact, their negative charge is going to push them apart. They're attracted to the water molecules. They're going to separate. So we're going to have 2 individual chloride ions. So we put the 2 out front because this is signifying that we have 2 ions, but they're not bonded together by anything. And as our products, now this is a solid. We're not going to expand it out. It's not dissolved. It's not dissociated. So we're going to leave that as barium sulfate solid. And we have the iron 2 ion dissolved in water. and 2 chloride ions also dissolved in water. So now we're going to take a look at this and we're going to see, are there any spectator ions? Is there anything that looks the same on the reactant side that it does on the product side? And so we can see that we have this iron ion here and we have this same iron ion over here. And we have 2 chloride ions here and we have 2 chloride ions here. These are considered spectators. Their state is not changing. Nothing is happening. They're not forming any bonds. They're not breaking any bonds. They're just watching the world go by. Okay, so we're going to leave those out. So in step 3, we're going to rewrite our equation, omitting spectators. Okay, so now we're going to rewrite our equation, but we're going to omit those spectator ions. So that means I need to include the sulfate ion. It was not a spectator. I need to include the barium ion, also not a spectator. And then I need to include the barium sulfate solid. And we've now written our net ionic equation. So pretty simple and straightforward. You will learn over time how to do this without this intermediate step. So let's go ahead and do another practice problem and see if we can't start moving in that direction. So our next problem that we're going to use as an example is the combination of lead nitrate and sodium bromide. So we have lead 2 nitrate. So our AP problem tells us that a solution of lead 2 nitrate, so solution, is combined with a solution of sodium bromide to form an insoluble lead 2 bromide. And since it was lead 2 and bromine is a -1, we're going to put a 2 here. And sodium nitrate. And we know because that's a nitrate, it's one of our SNAP rules, and it's sodium, that that is going to be soluble. Okay, so first thing we're going to do is come and see if we need to balance this equation. So I see over here, this is my most complicated compound, so I'm going to start with this one. I can see that I have 1 lead, but I have 2 nitrate ions here. So I'm going to come over here and put a 2 in front of the sodium nitrate to balance the nitrate ions. And when I do that, I find that I have 2 sodiums here, but only 1 on this side. So I'm going to put a 2 in front of my sodium bromide. And when I do that, that accounts for the 2 bromide ions here, and our equation is now balanced. So the next thing we're going to do is write it out with all of the ions. So we have our lead 2 ions in solution and 2 nitrate ions also in solution being combined with 2 sodium ions in solution and 2 bromide ions in solution to form insoluble lead 2 bromide and 2 sodium ions and 2 nitrate ions. We go through the same process again. Do we have anything that is on both sides of the equation? And the first thing I see is that these 2 nitrate ions are on both sides. And I see that these 2 sodium ions are on both sides. And so now I can rewrite my equation, omitting those spectator ions. And I write it as lead 2 ions in solution combined with 2 bromide ions in solution to form insoluble lead 2 bromide. Now you might be reaching a point where you can look at this equation, this initial equation, and you can see that you have lead here and lead here and bromide here and bromide here. And maybe you're starting to make the leap that you can see, oh, I have lead 2 ions coming from this, and those are aqueous. And I have 2 bromide ions coming from this, and those are aqueous. And that gives me lead 2 bromide that is a solid. Okay, it's okay. If you're not ready to make this jump, keep doing it this way. Make sure that you're always omitting the spectators. Okay, let's take a jump to, so far we've been doing precipitation reactions. There's another time that we write net ionic equations, and that's in the other type of double displacement reaction that we've talked about, and that is acid-base reactions. So let's take a look at a net ionic reaction in an acid-base circumstance. So now we're going to talk about a reaction between an acid and a base. So we are going to talk about the reaction between hydrochloric acid and let's do barium hydroxide. Okay, so we have our hydrochloric acid. This is our acid. This is our base. We know that every time we have an acid-base reaction, it's always going to produce water, and it's going to produce some salt. And that salt is going to be the cation from one and the anion from the other. So we have barium chloride, but barium is a +2, so I need 2 chloride ions. This is soluble, so I'm going to go ahead and put an AQ here, and water is a liquid. Okay, now I'm looking at this and I can see that my equation is not balanced. So I'm going to go back and go ahead and balance it. I have 2 chloride ions here, so I'm going to put a 2 in front of my hydrochloric acid. That gives me 2 hydrogen ions, and I have 2 more hydrogens here. So if I put a 2 here, that gives me 4 hydrogen to balance the 4 hydrogen, and it gives me 2 oxygen to balance the 2 oxygens, and the bariums are already balanced. So now my equation is balanced. Now I need to rewrite my equation, writing the electrolytes as ions. This is a strong acid. It's going to dissociate completely in water. So I'm going to have 2 hydrogen ions and 2 chloride ions. And I'm going to have a barium ion and 2 hydroxide ions. And that's going to form. Now here's where we don't have a precipitate. We don't have a solid, but we do have something that doesn't dissociate in water, and that's water. Okay, this is a molecular compound. We don't write it as a dissociated compound. So we have 2 water molecules, and we have a barium ion dissolved in water and 2 chloride ions dissolved in water. Okay, now same process. We're going to go through and see if there are any spectators that are the same on the left and on the right. So we can see that our chloride ions are the same on the left and on the right, and that our barium ion is the same on the left and the right. And so our rewritten equation that omits the spectator ions is going to be 2 hydrogen ions dissolved in water plus 2 hydroxide ions dissolved in water yields 2 water molecules. If you have a strong acid and a strong base, the net ionic equation for an acid-base reaction is always going to be hydrogen ions plus hydroxide ions makes water. Now, if you have weak acids or weak bases that don't dissociate completely, then we're starting from a different place. So we'll talk about those as an exception. All right, let's do one more just like that, and then we'll talk about that exception. Okay, so we are going to talk about sodium hydroxide, NaOH, in solution, being titrated with sulfuric acid, H2SO4, also aqueous, also a strong acid, but we're about to see one of the funny little things about this one. Yielding water, because it's an acid-base reaction, and sodium sulfate. And because it's sodium, we know it's soluble. NaSO4, sulfate is -2, sodium's +1. I needed 2. Okay. So sodium sulfate, I can see that I need a 2 here. That gives me 2 hydrogens, and 2 more hydrogens is 4 hydrogens. So I'm going to put a 2 here. That gives me 2 oxygens, 2 oxygens, 1 sulfate, and we're all balanced. Okay, let's talk about writing these as ions. So sodium hydroxide dissolves completely in water. So I have 2 sodium ions and 2 hydroxide ions, both dissolved in water. Now, when we talk about sulfuric acid, we always talk about sulfuric acid as one of our strong acids, but only the first dissociation of hydrogen from sulfuric acid is strong. The second one is weak. And so we're actually going to write this as H+ ions plus an HSO4- ion. Okay, so this is something new and different. And we still have our 2 waters over here and our sodium sulfate. This one gets a little challenging and a little tricky, doesn't it? When this HSO4 encounters one of these hydroxide ions, it's actually going to pull that H off. But just in solution, it exists this way. Okay, so what spectators do we have? What do we have that's the same on both sides? Oops, I forgot to write my sodium sulfate dissociated over here. Let's fix that. 2 sodium ions in water and a sulfate ion in water. Okay. So when it comes to crossing these out, what spectators do we have? Well, I have 2 sodium ions over here and 2 sodium ions over there. And nothing else is the same on both sides. And so I have to keep all of the rest of it. So I would write the 2 hydroxide ions in solution plus a hydrogen ion in solution plus a hydrogen sulfate ion in solution yields 2 water molecules and a sulfate ion in solution. So we can have simple net ionic equations. We can have slightly more complex net ionic equations. It's important that you recognize that weak acids, like the HSO4 ion, don't dissociate fully. And so we don't write them dissociated. They're not strong electrolytes. We only dissociate strong electrolytes when we're writing net ionic equations. Okay, so that covers net ionic equations. As always, if you have questions, let me know. We're going to move on and we're going to talk about particulate diagrams. Okay, so now we're going to talk about particulate diagrams. They're just another way of representing reactions. So we have talked about molecular equations. We have talked about net ionic equations. This is really exactly what it sounds like. It's a pictorial diagram. It's a graphic way of representing what's happening in a reaction. It's important that when we draw particulate diagrams, that we still maintain that stoichiometric accuracy. And so we need to make sure that we are representing whether things are in excess or whether they are in the appropriate molar ratio. So let's go ahead and talk about an example. So we're going to talk about the reaction of carbon monoxide with oxygen. And so here is our carbon monoxide. So we have carbon and oxygen, and we'll have a couple of oxygen molecules here. Okay, so if the red is our carbon, that means that this is our carbon monoxide molecule, CO, and that these are our oxygen molecules. So when we go to draw the products of this reaction, we want to make sure that we represent it accurately. And so let's just go ahead and write the chemical equation. We would have carbon monoxide plus oxygen is going to yield CO2. But this is not balanced. So I'm going to put a 2 here, and I'm going to put a 2 here. Now I have 2 carbons, 4 oxygens, and 4 oxygens. So now this is balanced. So I know that for every 2 molecules of carbon dioxide, I'm only going to use 1 molecule of oxygen. And we can really, the reason that we do these diagrams is because we can really see this graphically. And so we're going to take this molecule right here, and we're going to put the carbon in the middle, and we're going to show that it still has its same oxygen, but it's gained another one. And we're going to take this one. I have another carbon, and it started out with 1 oxygen, and it gained another one. Now, I have now used both of these, and I've used one of these because I've split it up, and I've given each of these carbon monoxide molecules and turned it into carbon dioxide molecules, so we now have 2. Can I react this one? I can't, because in order to transform this carbon monoxide into a carbon dioxide, I would need to have 2 carbon monoxides so that each one could take 1 oxygen from an oxygen molecule. And because I don't have the stoichiometrically appropriate ratio, I'm still going to have some carbon monoxide left over. So I'm going to have 1 carbon monoxide left over, and I'm going to have 2 oxygen molecules left. Okay, so that's what I mean by being stoichiometrically appropriate. You want to make sure that you don't create something that would then cause you to have a half of an oxygen molecule, because we can't have that. It doesn't happen. So this is our process. We want to make sure that we show our excess reactants in addition to our products. Okay, let's do one more example, or maybe a couple more examples of this one. Let's look at, instead of a synthesis reaction, let's look at a decomposition reaction. So let's look at the reaction between the decomposition reaction of hydrogen peroxide, sorry. So when hydrogen peroxide decomposes, it decomposes into water and oxygen. Okay, so let's take this molecule, and we have 2 oxygens. I guess I should have created a key. Oxygen, and our blue is hydrogen, so that these are hydrogen peroxide molecules. Now we know that we need to have in our water molecule 1 oxygen and 2 hydrogens. That leaves me with 1 oxygen still hanging out. So I can take that oxygen and I can pair it up with the oxygen from another one, and I can have 2 oxygen atoms together to make an oxygen molecule. And that leaves me with the 1 oxygen and 2 hydrogens to make 1 more water molecule. This can't decompose, because in order for this to decompose, I would need another hydrogen peroxide molecule so that we could take an oxygen from each to make this oxygen molecule. And so I have excess hydrogen peroxide left over at the end of my reaction, We can also do this numerically or in an equation by saying the hydrogen peroxide molecules decompose into water and oxygen gas. And in order to balance this, I need to put a 2 here and a 2 here. So I took 2 hydrogen peroxide molecules and made 2 water molecules and 1 oxygen molecule. And since I have 1 hydrogen peroxide molecule, that's my excess reactant. So again, this is just a different way of looking at the same information. All right, one last one. We'll look at an acid-base reaction this way as a particulate diagram. So let's take a look at an acid-base reaction. We'll make it a simple acid-base reaction. We'll make it hydrogen chloride. So we have H, and we'll go ahead and make this be Cl. So we have little blue circles are H's and big green circles are Cl's. And then let's go ahead and have a sodium hydroxide. So a O and an H and an Na. Okay, so now we have Na and we have O. So my question to you is this. Is this what we would actually have in water? No, because what we would have is dissociated ions, right? So we would have hydrogen ions floating around, lots of little hydrogen ions floating around. And we would have lots of chloride ions floating around. And our sodium hydroxide is going to dissociate as well. And so what we have here is a hydroxide ion, OH minus. We should have a few more of those. This is our OH minus ion. This is our OH minus ion. And now we just need some sodium ions floating around in solution. Na plus, sorry, the black marker's running out. Now, obviously, these would be in 2 separate containers because as soon as we combine them, what are we going to get? We're combining an acid and a base. So we're going to wind up with water molecules. So let's see. I have 1, 2, 3, 4 hydrogen ions and 1, 2, 3, 4 water molecules. And so I'm going to wind up with, or hydroxide ions, I am going to wind up with 4 water molecules. And I'm also still going to have chloride ions floating around in the solution, and sodium ions. So it looks a little different when we talk about a solution and instead of gaseous reactions, but they can still be represented with particulate diagrams. I hope this helps. If you guys have questions, let me know. We'll be practicing these in class tomorrow.